let us continue with our lecture. The magic of gauge invariance. Yesterday we began and discussed Lorentz invariance, which requires the validity of gauge invariance in the form of the Watt identity, because the Watt identity holds processes like Compton scattering are Lorentz invariant, even though the polarization vectors epsilon do not transform in a Lorentz covariant way. So that is what we saw yesterday, and today we will discuss two further consequences of gauge invariance which are similar. And the next one is the independence of the gauge fixing parameter psi. You know that we needed an unphysical gauge fixing term in the Lagrangian. We took the following so-called gauge fixing term, minus 1 over 2 psi d mu a mu squared. And in our practical calculations up to now, we set psi equal to 1. Therefore, there was no appearance of psi in our formulas, but in principle, in the beginning, we had a general gauge fixing term depending on psi in our Lagrangian. And that was necessary in order to quantize the massless spin 1 field, the photon field, in the Gupta-Bloiler formalism. And so now let us investigate what is the role of the psi. Obviously, psi must be unphysical, and it would be strange if observable quantities like cross-sections would depend on psi. They should not, but let us verify that they actually do not depend on psi. So in order to do that, we need to repeat some calculations with general psi dependence. And first, the psi, if we leave it open, it will appear in the free Lagrangian for the photon, and therefore it will appear in the quantization of the free photon Lagrangian. And I write it now in this form, which I already announced once, namely in a schematic way, where we have a bilinear term, a mu, and in between there is a differential operator d mu nu. We can always bring the Lagrangian into this form because it is bilinear in the photon field, and by partial integration of these terms we can bring it into this form. And the differential operator, if we have general psi, is then the following: g mu nu times the D'Alembert operator minus d mu d nu plus 1 over psi d mu d nu. So you see that the first two terms, they are the ones coming from f mu nu, and the second term is the one coming from the gauge fixing term here with 1 over psi. Then we have a recipe to obtain the propagator, which we go through now. We take the Fourier transformation of the differential operator, where we replace I times derivative by a momentum. Then we get here minus, how do I write it? Let's say minus p square times, from the first two terms, g mu nu minus p mu divided by p square. Okay, so this is the Fourier transformation of the first two terms, and I factor out here p square to make it more convenient. And the second term is then minus 1 over psi p mu. So this is our Fourier transformed differential operator. And then we need the inverse. The inverse of the Fourier transformed differential operator gives us our propagator for our Feynman rules. That was the general recipe. So this propagator here with indices mu nu is given by I times p tilde mu nu, which is the inverse of the Fourier transformed differential operator. And here we can just read off the inverse of that. So it's quite easy, even though it looks complicated. That is a projection operator, and that is the orthogonal projection operator. And then the inverse is just the inverse of the coefficient of the first projection operator and the inverse of the coefficient of the orthogonal projection operator therefore, and then I multiply by I. So we get minus I divided by p square, so the inverse coefficient, times this projection operator. And here also the same thing, minus I over p to the fourth times p mu. Times psi. Psi p mu. So again, the inverse coefficient of this projection operator, and you can easily check that the product of the two is simply the metric tensor g mu, everything else completely drops out. So that is the inverse, and that is the propagator Feynman rule for general psi. And just to make the connection to what you know before, we had psi equal 1. For psi equal 1, this term here drops out, and also here psi equal 1, these two terms drop out, and what remains is just minus I g mu over p square, which is exactly what we always used. But all of this is an additional term which we have for general psi. Yep. Here p to the fourth, and here also p to the fourth over 1. Here p square, yes. So that is a projection operator. That means if you square this operator, multiply it by itself, you get the same operator back. That is why it's useful to write that thing in this form. Then inverting it becomes a piece of cake. So that is now our propagator Feynman rule, and let us use that to recalculate a process which depends on such a propagator. So Compton scattering does not involve an internal photon propagator, but our other process, E plus E minus 2 mu plus mu minus, this contained such a propagator, and so we can now look at that process once again. So here is this process for E plus E minus 2 mu plus mu minus with this propagator, and this has now the following structure. So we already brought it to this nice form where we have these current-like quantities, E mu for the electron line times m mu for the muon line, and then we multiply with the photon propagator, and now we plug in this more complicated expression for the photon propagator, which becomes here using again q as the variable. So let's write q square in the common denominator of all of this, and then in the numerator we have the metric tensor g mu mu. Let's say plus, simplifying a little bit, q mu divided by q square, and that additional new term comes with the following coefficient. It comes with the coefficient psi minus 1. And again, for psi equal 1, that extra term of course vanishes. But this is the difference to what we had before. Now the question is, does that process, the physical matrix element for the probability amplitude, does it depend on psi or not? And so let us look at the difference to the case we had, that was section 4.3. What are the different terms? The different terms are of course those ones coming from this q mu times a factor. So the point is that we get now a contraction between the electron line E mu times the photon momentum q mu. So we get terms, one term looks like this. Actually, it's a factor. And another factor, q nu times the muon line. So all the new terms which differ from what we had before involve factors like this. Therefore, what we should look at is what happens if you contract an electron line with a photon momentum, or if you contract a muon line with a photon momentum. And if you remember the exercise sheet, there you are supposed to calculate exactly that for a scalar field line where you have E plus E minus two scalar fields. And for that, there is again an identity which we can also call a Watt identity. And this identity, again, is a reflection of gauge invariance, and the identity is, of course, nothing else than this contraction actually vanishes. We get 0 if you contract such an electron line with the associated photon momentum, and for the muon line, of course, we have the same thing. So let us prove this. How can we prove that? Well, let's plug it in. For the electron line, for example, we have here V2, as we called it, bar for the incoming positron times gamma mu times u for the incoming electron. And I neglect some factors, E times Q, which are not important. And then we contract with the photon momentum Q mu. That is our expression corresponding to that contraction here, where the E mu, again, corresponds to that electron line. And maybe I repeat briefly what we need to do: go against the direction of the arrow and collect all the structures. So we start with the spinor for the incoming positron, which is V bar. Then we have the gamma matrix from the vertex and the U spinor for the incoming electron. So that is the expression that we need to investigate. And now, how can we investigate it? I told you already what is always the trick for such Watt identities. You see, you get here again a Q slash. And this Q slash should be replaced by the difference between the two associated momenta. So which momenta can we take here? So kinematically, Q flows in this direction, and here we have P1, and here we have P2 incoming. So Q can be replaced by P1 plus P2. So let's replace Q slash by P1 slash plus P2 slash. But then I can also enhance the trick a little bit more. I can write P1 minus M and P2 slash plus M. Then it's still the same as Q slash. But what happens if I plug in this combination into that position in the spinor line? Then the P1 slash minus M stands here and it hits the U. U is an eigenspinor of P slash 1 and it satisfies P slash 1 minus M, U equals 0. So therefore this vanishes because of the U. And here, of course, V bar satisfies V bar acting on P2 slash plus M gives also 0. And therefore both of them vanish. And therefore we get 0. That is the simple proof of this. Again, the same strategy as always in the context of those Watt identities. So, and that means that the terms in our matrix element for Feynman diagram, which have to do with the gauge fixing parameter psi, they drop out because of the Watt identity. In other words, gauge invariance in the form of the Watt identity guarantees that our physical scattering matrix element is independent of the way we do the gauge fixing. And that is obviously a very important result for the physical interpretation of the theory. So let us write it down. TFI is independent of psi. And the term for this, we call it gauge independence or gauge fixing parameter independence. Gauge fixing independence. So this is not the same thing as gauge invariance. Gauge invariance would be when we can do a gauge transformation and the Lagrangian stays invariant. This Lagrangian has broken gauge invariance, but the physical result is independent of the gauge fixing procedure, and so that is what we mean when we say gauge independence of the physical result. And if that were not true, we would have difficulties in interpreting the theory. Maybe we would say psi is a new physical parameter which should be measured, but that is not what we want. And so anyway, this is a true statement, and of course this we have proven it for that example, and it's true in general, but this is something beyond our lecture. So the next point, and the last point in our list of magical relations for gauge invariance, will come after the next question. So. So are you talking about this? This is what the spinors satisfy. So they satisfy the Dirac equation P slash minus M on U equals 0. That is the Dirac equation, which has absolutely nothing to do with gauge fixing. I don't know what you are referring to, but I will say some comments. But first of all, that quantization of the spin 1/2 fermions, which leads to the spinors, is of course absolutely independent of the quantization of the photon field. The photon quantization depends on psi. The spinor quantization has nothing to do with psi, first of all. So this is not depending on the gauge fixing at all. And at this level here, we are on the level of free fermion fields, which know nothing about interactions. Okay, but then indeed, we have to define our spinors, and they must satisfy the Dirac equation in momentum space if we want to write down an operator field psi hat, as we called it at the time, which is this dp tilde integral of, I don't know, sum over s u of p comma s e to the minus I px times creation or annihilation operator. This sort of thing. We needed that the operator field satisfies the Dirac equation in position space, and in order to achieve it, the spinors here must satisfy the Dirac equation in momentum space, so they must satisfy p slash minus m u equals 0, and similarly p slash plus m on v equals 0 as well. That is a must. So that was not our choice. What was, for example, our choice, and maybe this is what you remember, is the normalization of the spinors. You can, of course, multiply the spinors with a normalization factor. That is your choice. And the normalization might then affect what is the normalization of the A, and so on. So you can shift around normalization factors. And there we had a choice, namely this sum over the spin of this combination. That gives p slash plus m. And that is a normalization choice. You could choose a different normalization where you get here a different factor, for example, divided by 2 times the energy or something like that. But we made the choice where we just have this. And again, the normalization is our choice, but the structure p slash plus m, that is again a must. It's an automatic consequence of the Dirac equation. That something like this has to appear maybe up to normalization factors. So maybe that was what you had in mind.
Okay.
No, we use the interaction in a very important way. We use the interaction in the way that we get Q slash between the two. That is very important. So we have two things going on, namely a specific form of the interaction which produces here the Q slash, and that is of vital importance. And once we have the Q slash here, we can manipulate it by momentum conservation, and then we can use the so-called on-shell properties of the spinors. So the second thing next to the interaction that we use is that we have physical electrons and positrons here, which are real free particles which can be observed in experiment, and therefore they are described by those spinors U and V, which satisfy the free Dirac equation. That is, for example, different from virtual electrons which appear in the middle of some Feynman diagram. So for these external electrons and positrons, we have those spinors which satisfy the free Dirac equation, and that together with a specific form of the interaction gives us the Watt identity. And you will discover something similar if you do the exercise for the scalar particle. There the interaction is different and you do not get P slash, or because there is no gamma mu. But you can also do the same or similar manipulation, and you use again the specific form of the interaction between photon and a scalar particle, and you use that the scalars are physical particles which satisfy a free Klein-Gordon equation in momentum space P square equal to m square in that case. And so again, interaction plus the free particle properties together provides the proof of the Watt identity. Well, we did, because we argued for many, many weeks that we need a gauge invariant interaction, and that is the result. That is why I stressed so much that we need a gauge invariant interaction. If you have a massless vector boson, a massless photon or massless spin 1 particle, its interactions must be gauge invariant. Otherwise, there is no consistency between the interpretation of the free photon as a particle and the interaction. And we have made sure here in QED that our interaction is gauge invariant. And therefore, all these nice properties follow. And if you would do it in QCD or in some more complicated theory like the standard model or extensions, if you again start from gauge invariance and make sure that your interactions are compatible with gauge invariance, then they are also they will provide those properties. And that is, of course, not an obvious statement. What I am saying now should be proven, and the proof is actually not a piece of cake. But the fact that the proof has been done means that those gauge theories are established as consistent quantum field theories for spin 1 particles, and that they can be used as a basis for elementary particle theories. So, and I want to use this section here to illustrate the important features. This is the second of our 3 important features which fall into this category of consequences of gauge invariance. We prove them all with explicit examples like here, but they are true in general. Therefore, let us now go to the third case. which is the unitarity of the physical S matrix. In a way, this is maybe the most mysterious or least obvious statement, but maybe the most important one for the interpretation. So let us begin with something from yesterday. Yesterday we saw in section 451 the following. If you apply the S matrix or S operator onto a physical state, in Compton scattering we had physical photon polarizations lambda equal 1 or 2 as opposed to lambda equal 0 or 3. So then this is independent of the representative of the equivalence class of the physical state. So we showed it concretely. If we change our polarization vector epsilon by something proportional to k, then that is nothing else than replacing our physical state by another representative of the same equivalence class of physical states in our language of equivalence classes. And we saw that the difference drops out. Therefore, we can use any representative of an equivalence class and always obtain the same matrix elements for physical processes. And so that means you can say that the S operator really acts onto equivalence classes, and you can define it consistently on equivalence classes by its action on any arbitrary representative. So it's defined consistently on our physical Hilbert space H physical as we defined it. This is the space of equivalence classes because the action does not depend on the chosen representative. So it's meaningful to speak of the S operator acting on equivalence classes as well. So this is the first statement that is of course important for the interpretation, and we saw it yesterday. And now the question is the S operator defined on that space of equivalence classes a unitary operator? That is the question. And why is this question important? What unitarity basically means is simply that probabilities add up to 100%. It simply means if you have one initial state and you sum over all possible final states for which you have a non-vanishing probability, then the sum of all probabilities is 1. That is what unitarity means. And the positive definiteness of the space means that each probability is bigger than 0 or 0 or bigger. You do not have negative probabilities, and unitarity then means the sum of all of these positive probabilities is 100%. And if those two properties are not valid, you cannot interpret the theory as a quantum theory with a probability interpretation. Therefore, this is absolutely vital in order to be able to interpret the theory. So let's write it down: probability of all physical final states in total is equal to 100%, and the converse is that the probability to find an unphysical final state is 0. So that is necessary for the interpretation. Okay, and so let me now write down, maybe let's write it at the other blackboard. So the question is unitarity on this physical Hilbert space of equivalence classes. And what is that? It is equivalent to the following statement. So let's say you have some physical state I physical and J physical. That is equal, so here I have just a matrix element, and unitarity means that the unit operator is equal to S dagger S, and therefore I can write this as the following sum over all basis states that I call F physical, basis representatives of our physical equivalence classes. And then we have here state I physical, S dagger, F physical, F physical, S J physical. So what you see here, what I wrote down, is basically a matrix version of the unitarity. So basically we have here S dagger S is equal to the unit operator, but I write it in matrix notation, so here I really have an explicit sum over all basis states in our physical Hilbert space. And from the left and right I also multiply with two arbitrary basis states of our physical space. So this relation, if it's valid for any I and j state, that is equivalent to unitarity on our physical Hilbert space, and that is the question. Now, as a contrast, I write down something else, namely unitarity on the full unphysical space, on the full space that I call V, including unphysical states. What means unitarity on the full space? So if that is not equivalent, but it follows that if we have a physical state here from the left and right, then we have basically a unitarity relation, basis F of the full space. And then I write down essentially the same thing. Okay. So here is a matrix version of unitarity, S dagger S equal unity for the full space, where I have here a sum over basis states of our full space. And the sum is of course meant in a general sense. It might also be integrals in case of non-normalizable states. Okay. And this second statement, unitarity of the S operator on the full space, that is true, known to be true, because by construction our S operator is given by this time-ordered exponential function, and the time-ordered exponential function is by construction a unitary operator, because we have E to be basically I to the Hermitian operator in the exponent. Therefore this is unitary, but the unitarity is only obvious on the full space, and if we do some restriction of the full space to some strange subspace, then the unitarity might be lost. And so therefore the second line here, that is valid, and the question is whether the first line is also valid. And now from the comparison, this is true and this is hopefully true. You see what we need to prove, namely basically we need to prove that here in this expression, if you sum over all the f's, it's the same as if you sum only over the physical f's. If that is true, this sum gives the same as the full sum, then the first line and the second line are equal, and since the first line and the second line is true, we then know the first line is true as well. So what we need to prove is that in this sum, all the unphysical states drop out amongst each other, and therefore the full sum is equal to the sum over physical states. That is what we need to prove. Let's make a box around this. So hence the question is equivalent to proving that the first line is equal to the second line. So, and that is what we can now investigate with the help of one example. Again, we just look at one example. One example process here. So this corresponds, of course, to a process, or also this corresponds to a process. Some physical state goes into some final state with an S matrix element, and that corresponds exactly to our Feynman diagrams. And so we look at one particular process, and we will look again at Compton scattering and look at the sums here just by taking only states corresponding to Compton scattering. And then we will see that for this example, it is indeed true that the first line is equal to the second line, and then we hope and guess that the same result will be true in general. So let's use as an example Compton scattering. So where we simply say that all these states I, J, F, they all correspond to an E minus gamma state of an electron and a photon. And in this case, this sum over all the final states F would correspond to all the possible states of the kind electron photon, and that involves an integral over all the final state momenta. It involves a sum over the spins of the electron in the state, and it involves a sum over the polarizations lambda of the photon in the state. This is for sure contained in this generalized sum over all the final states F. And now, since we have here in the general case, we have a Hilbert space, which is not a proper mathematical Hilbert space, but a space with negative norm states. In this summation over a basis, we also need to put plus minus 1. Plus 1 for positive norm states as usual, but the minus 1 applies for negative norm states. So because of the negative norm, they appear here with a minus in this generalized sum over all the basis states. So, and then we can write down what is actually our first line concretely for Compton scattering. So everything now is a Compton process. So then the first line, the only thing which is important and interesting for us is of course the photon polarization sum. Everything else here is the same between first line and second line, and for the photon polarizations in the first line we have only physical lambdas, 1 and 2, and in the second line we have all lambdas, namely 0, 1, 2, 3. That is exactly the difference. And so let's write the main part of the first line, which is then the photon polarization sum over lambda from 1 to 2 physical lambdas, and then basically we have the first factor is a physical matrix element complex conjugated T star Fi. That is the first matrix element, and the second one without star is then P Fj. And so obviously here I suppress all the indices, but the matrix element is exactly the matrix element for Compton scattering that we have discussed a lot now. And the final state has a photon with polarization lambda, and we sum here in this combination over all possible photon polarizations lambda. And in the second line, we have analogously the following. We have the same prefactors, and then we have the sum over lambda equals 0, 1, 2, 3. That is the difference. And then we have Tfi star Tfj. And now we also have the thing with the negative norm. So we have here times minus the metric tensor lambda lambda, which is exactly minus 1 if lambda is 0, which has negative norm, and plus 1 in all the other cases where we have positive norm. So, and that is the difference. And so what we need to prove, as we said, we need to prove that actually the first line is equal to the second line. because the second line behaves in a unitary way. And so is the first line second equal? And of course, now you see maybe already the structure which emerges. It is essentially the same structure that we also encountered when we looked at the polarization sums for photons. And there we had exactly the same discussion. So we can now repeat it. And of course, the answer is this is equal, and the unphysical lambdas here drop out. So let's make it manifest. So this is analogous to the following section, namely 442. There we had again the Watt identity for Compton scattering, and then exactly with this prefactor G lambda lambda, we have here epsilons with polarization lambda, and this sum over all the 4 epsilons with this metric tensor is equal to the sum over lambda equal 1 and 2, because there was a Watt identity telling that this m mu nu times epsilon for polarization 0 is equal to minus m mu nu times epsilon nu for polarization 3, right? That was basically the relationship that the Watt identity gave us, and because of this, including the different sign here, the lambda equals 0 and 3 drop out, and therefore, indeed, first line is equal to the second line. And then we get a nice conclusion. The nice conclusion, the moral of the story is unitarity holds on our physical Hilbert space H physical in this example. And therefore, the probability interpretation of the theory is possible and consistent. That is the important result of this discussion of the unitarity of the S matrix. So the physical S matrix restricted onto the space of positive norm states which have a correct physical interpretation is unitary. All the physical probabilities add up to 1. All the unphysical probabilities add up to 0. And therefore, this is the ultimate proof that our interaction that we have proposed here with this gauge invariant interaction term remains consistent with our interpretation of the theory. And clearly, we have done only example proofs, but the proofs can be generalized, and they are not only valid for QED, but also for other gauge theories, where the proofs become step by step more and more complicated. But nevertheless, I wanted to show you here what are the issues, so that you understand what are the questions that one should ask, and you also see an indication that it's actually possible to answer all those questions in a positive way. So a very nice reference where you can read more about all of this is, I would say, the book by Kubo, which I already mentioned. And another book which is very nice also is a book on gauge theories by Aitchison and Hay. But and a third book which is also nice and where you also can find this is Böhm, Benner, Joos. But of course the topic is quite standard, so you will find it in all books on gauge theories, but I would say these are particularly noteworthy because they contain nice and detailed explanations of what I've also tried to explain in this section here. Change of gears. Let us now come to the final chapter of our lecture. I want to give you some small outlook to the theory of higher orders. higher order Feynman diagrams with closed loops, where aspects like divergences, renormalization, regularization matter. But I do not want to give the full theory, that is also not possible because of lack of time. But what I want to show you is the principles that you see what can happen if you take into account higher orders, namely why and how do the divergences manifest themselves, how can we get rid of them in a consistent way. The theory of renormalization in general is of course a procedure where you replace the divergent expressions by finite expressions, but in such a way that the result is physically sensible, meaningful, and consistent with the basic axioms of quantum field theory, and so that you get a predictive and also consistent theory where interpretations like the ones that we have just discussed all remain valid also at higher orders. But in particular, in the last 3 lectures, I want to show you that higher orders are not only about technical details like divergences and mathematical tricks, but there are very, very important physical phenomena coming into play which arise at higher orders, and those are quantitative changes compared to lowest order predictions, of course, but in particular also qualitative changes, really qualitatively different behaviors which you might not guess from looking at lowest order results, and it's in particular those that I want to discuss here, at least with the help of some examples. So this is chapter 5, basic properties of higher order corrections. So we want to discuss divergences and renormalization. We want to discuss physical phenomena at high and low energies. And we will do all that with the help of some simple examples, which are sufficient to show you that there are interesting new phenomena. And so, of course, we will remain to work in QED. And so, therefore, let us start by giving ourselves an overview of QED one-loop Feynman diagrams. And actually, let me announce immediately the simple example that I want to look at, so that you are not surprised afterwards, is the so-called photon vacuum polarization. Basically, this is what we want to analyze, and it will illustrate all of the above. So, QED one-loop diagrams, let's begin by looking at an overview. Let's stick with the process E plus E minus to mu plus mu minus, which is better than Compton scattering here in this case. What are the Feynman diagrams that appear at the one-loop order for this process? Okay, so first of all, the tree-level diagram is this. So this is tree-level. And now let us write down some one-loop diagrams. Who has an idea how such one-loop diagrams could look like? Okay. Like this. And this is actually already the photon vacuum polarization, which we will focus on. And another name for it is the so-called self-energy of the photon. But at first, let us write down some other Feynman diagrams, because this is not the only one. Yep. And then? Like this. Okay, this is true. This is an important Feynman diagram, which is also of higher order, but we would not classify it as one loop. But it's also important. It's important for the physics discussion of the process, indeed. So, but we will not consider it in this lecture, and also not in this semester. And it would be the so-called real radiation of extra photons, which then appear in the final state. And sometimes it happens that these real radiation photons are undetected because they are too close to the final state electrons or something like this. And then experimentalists cannot distinguish this process from that one. And therefore, it indeed, even if we are interested only in the plus or minus 2 mu plus mu minus, we have to take into account those Feynman diagrams as well. But they are not one loop order, and therefore today let us not consider them. But there are some one loop diagrams. This, right, and there are 4 diagrams like this. You can do this on all the external fermion lines, and they are called external self-energy corrections. And actually they require special treatment, which also goes beyond this lecture. So this is connected to the so-called LSZ theorem for S-matrix elements, which I mentioned, which is the more general approach to S-matrices than the one that we have used here in the lecture. This LSZ reduction tells us exactly what we need to do with those Feynman diagrams. Something else? Okay, this is a so-called vertex correction. You also had an idea, Mr. König, I think. Same idea. Okay. Anything else? So there is also a vertex correction for the muon, which looks similar but mirrored. Anything else? There is one more class of diagrams. The so-called box diagrams. And there are 2 of them. One of them would look like this, and the other one is a cross box, let's say. So they are kind of a little bit more complicated. But this is the complete list. This is the complete list of one loop diagrams for this process, and so here you have an overview of the types of diagrams that exist. You have self-energy corrections for internal lines, for external lines. You have vertex corrections, and you have box diagrams, and in general, so this is often the type of diagrams that you have, but sometimes there are even more complicated types of Feynman diagrams. So that is nice, and now let us focus on the photon self-energy, or the photon vacuum polarization, which is the one that we will compute. All the other ones we will not compute, but this is the one that we will really compute explicitly. So that is the photon self-energy. So this Feynman diagram here has a special role. And that is also the reason that it makes actually sense to consider just this single Feynman diagram and neglect all the other ones. Because normally it does not make any sense to just consider one single Feynman diagram, because only the sum of all Feynman diagrams is an amplitude, a scattering amplitude, which makes sense. But in this case, there is an exception, and this diagram on its own makes sense. And the reason is, we can assume here that this fermion in the loop is actually some new fermion, let's call it F, a new type of fermion F, which is maybe neither the electron nor the muon, but something new. Or maybe even F is equal to electron or muon. But the type of the fermion here in the loop doesn't matter for the existence of the diagram, and that makes this diagram special. So it is the only diagram with a fermion loop. Right? All the other diagrams do not involve such a loop consisting only of fermions. And if there is a new fermion species F, which might have a charge QF, which might be also -1, but it might be just also a different charge with some value which we don't know. Then this diagram would be exactly the only Feynman diagram which depends on the new charge QF, because that vertex here will be proportional to the charge QF, and so the diagram is proportional to QF squared, where all the other diagrams are independent of the new fermion charge QF. Only diagram proportional to QF squared. And so therefore, since perturbation theory is basically a power series expansion, it always makes sense to consider one certain order in the expansion. And here, this single diagram corresponds to the order QF square. It's the full set of all QF square diagrams, and therefore it makes perfect sense as an isolated contribution. So we can say this diagram forms a consistent subclass of contributions, of one loop contributions, namely the correction of order QF square. And this means that the diagram is consistent with the theory of renormalization with Ward identities and so on. Consistent with respect to Ward identities, renormalization. Etc. So all kinds of properties which hold order by order in perturbation theory, they must all hold individually for this single Feynman diagram. And of course, Ward identities, whatever they might be at the one loop level, but Ward identities will hold at all orders in perturbation theory. Therefore, they will hold exactly at this order. Therefore, this diagram on its own satisfies appropriate Ward identities. Similarly, renormalization works order by order. Finiteness, consistent definition of finite results works order by order. Therefore, it works individually for this single Feynman diagram and so on. Therefore, it makes perfect sense to consider this diagram in isolation. And of course, the diagram will lead to very interesting and also important physical effects, which we want to discuss. And so let us look at the building block of this diagram. So the diagram in particular contains this subdiagram here. It, instead of the photon propagator that we have here in the tree-level diagram, we now have this combination instead. And let us look at exactly this combination here, which is the essential point. This combination here is a product of photon propagator times the loop times another photon propagator. Let's give some indices, mu nu, like before. And then here we also have a new vertex with Lorentz index rho. Here we have a vertex with Lorentz index sigma. And through the whole thing, there flows the momentum q, which is the photon momentum. And then what we get here, again for gauge parameter psi equal 1 for simplicity, we have minus I g mu rho, first of all, divided by q square. Okay? This is the left photon propagator. And then from the loop, we have something which we need to calculate, but we give it a name. Let's call it minus I sigma rho sigma of q. Sigma stands for self-energy, and then the other photon propagator minus I g sigma mu divided by q square. Okay. And then, so this is the right photon propagator, the left photon propagator, and this is whatever is the remaining result of calculating this quantity here in the middle, the loop. And clearly the loop will depend on the photon momentum which flows into it, and it will depend on the two Lorentz indices, and everything else is unknown. So we give it a name, sigma rho sigma of q. And the prefactor minus I is kind of motivated because also the propagators have minus I as prefactors. So that is what we want to calculate, and so in this way we have defined the important building block. So this object here, which just contains the vertices and the loop, but not the external photon propagators, this object is minus I times sigma rho sigma of q, and this is the so-called self-energy. This is the so-called photon self-energy. And the Feynman diagram, which defines this sigma, the self-energy, so the Feynman diagram is just the block containing the vertices and the electron propagators here, but not the external ones. And this block, such a building block, is called a one-particle irreducible Feynman diagram. This is a one-particle irreducible diagram, or part of a diagram, you could also say. And one-particle irreducible means that the diagram here, this part, remains connected even if you cut one line, remains connected if one line is cut. Okay. This is the definition of one-particle irreducible. So that is the photon self-energy. It is a quantity with two open Lorentz indices because it has two outer vertices which both depend on the Lorentz index, and it depends on the momentum q. Good. And it's defined by this one-particle irreducible part of the Feynman diagram. That is not yet the so-called vacuum polarization. The vacuum polarization is a simpler object which we are going to define now, which is basically a part of the self-energy. So let's define the photon vacuum polarization. And in order to define it, we first need again a claim about the so-called Ward identity, which is again an identity of the kind that you have now already seen many times. Namely, we claim the following: the just defined photon self-energy, which I now, for simplicity, write with indices mu nu, satisfies q mu contracted with sigma mu nu gives 0. So, and this is now not surprising to you because you've seen exactly many identities where a contraction with q mu gives something interesting, mostly 0. And here again, this is the case. And that means here that the photon self-energy with these two indices is basically orthogonal in a way to the momentum, and we call that transverse. So that is what we mean when we say the photon self-energy is transverse, so it satisfies exactly this equation. And the proof we will give later. So let's assume it for now. And assuming that this is true, we can derive a consequence, namely sigma mu nu of q must have a certain Lorentz structure. We know that this thing is Lorentz covariant, so it has correct Lorentz transformation properties. It has two open indices, and it depends on q. So on the right-hand side, there must appear some combination of objects with indices mu nu, which have a Lorentz invariant or Lorentz covariant transformation property. So on the right-hand side, there can only appear q mu or the metric tensor g mu. There is no other object available with open Lorentz indices mu nu. So there must be something proportional to g mu nu and something with q, and that could be q mu, q nu. Each of them with some coefficient. Okay. So that is what must happen of Lorentz covariance. And now, because of transversality, the coefficients are related, because if I contract with q mu, I get from here q mu. If I contract this, I get q squared times q nu. So we can do this q squared times g mu nu. Now when I contract this with q, I get q squared q nu. If I contract that with q, I also get q squared times q nu. So actually what we see is that the whole result must be proportional to exactly this combination, because that is the single only possible combination of covariant terms which is transverse. And therefore this combination must have a common coefficient, and the common coefficient is some function which has no open Lorentz index anymore, so it can only depend on the scalar product q squared. And that function is called pi gamma of q squared. And that is the vacuum polarization. So this pi gamma of q squared is now a scalar quantity. So it is simpler. And that is the so-called vacuum polarization. So in this way, assuming the validity of the water identity, we can define this important photon vacuum polarization. This is the most important definition, but let us play around a little bit with the definition and use the right. We can define this important photon vacuum polarization. This is the most important definition, but let us play around a little bit with the definition and derive a simple consequence. And we derive this consequence in a general number of dimensions, let's say d dimensions. Let's do it in d dimensions, where d is a general number. And let us look what happens if you do the following, namely a contraction of the two indices of the photon self-energy, mu, mu, contracted over mu. What happens? On the right-hand side of this definition of the vacuum polarization, we can now contract the indices. So in the bracket, the first term is q squared times what? The first term is the contraction of the metric tensor with itself, and in d dimensions, that is d, the number of dimensions. q square times d. The second term contracted is just q square times 1. So q square times d minus q square. And that times the vacuum polarization. And therefore now we have a scalar prefactor, which is a number, so we can divide by the prefactor, and then we obtain an explicit formula for the vacuum polarization pi gamma of q square is equal to, first of all, 1 over d minus 1 times 1 over q square times that contracted photon self-energy. And so this can be used as a formula which gives us a calculational recipe to directly calculate the photon vacuum polarization. And then this will be simpler than calculating the self-energy with two open indices, because here we have no open index, and so this will lead to contractions of gamma matrices where we can use simplifications like yesterday and so on. Now let us come to the first role of the vacuum polarization. What does it actually do in the Feynman diagrams, and how does it modify predictions between tree-level and one-loop order? And in order to see this, we look at a more complicated situation for a short while in order to understand really the deeper role of the vacuum polarization, because there is a certain so-called resummation possible. Resummation is the term which is used if we sum infinitely many Feynman diagrams of a certain kind. And here I propose to sum the following infinite number of Feynman diagrams, namely the photon propagator at tree-level plus this loop-corrected photon propagator and so this is obviously what appears in our one-loop correction, exactly this combination, tree-level plus that one-loop term. But now we can go on at the next order. We would also be able to have this Feynman diagram with 2 times the self-energy next to each other, and then it goes on 3 times the same self-energy plus and so on. So there is an infinite tower of Feynman diagrams of this sort. So there is an infinite number of diagrams. These are of course not all Feynman diagrams, but it's a special class of Feynman diagrams, and there is an infinite tower resulting from this class. And let's look at this particular class of Feynman diagrams, which is basically answering the question, what is the role of this particular loop in the all-order expression of the theory? And so let's look at the summation of this. So what happens? So this propagator is minus I g mu nu divided by q square. So we have here indices mu nu on the left and right. We have to do that consistently everywhere. In every diagram there is mu at the very left and mu at the very right. So then the second diagram is what? So here we have, like before, we have here minus I g mu, let's say, rho divided by q square for the left propagator. Then we have minus I, the self-energy, which is now, however, minus I times g rho sigma q square minus q rho q sigma times pi gamma. This is now the self-energy, and then times the other photon propagator g sigma nu divided by q square. And so on. So you can guess how the other terms would look like. They would involve several factors which look like this. So the second diagram involves exactly the same as the first, and then times once more the same kind of factors, but just with other Lorentz indices, such that we get a matrix contraction of all the Lorentz indices. Let's evaluate it. In the evaluation, you should recognize that the terms with the metric tensor, they behave in a really simple way. Let's ignore the terms with the momenta, explicit indices here for a moment. So let's say plus terms with q mu terms. So for example, this term here, you will get q sigma times metric tensor. So that gives q mu, and the q sigma becomes q nu, and so on. So there are some terms with explicit momenta. But let's look at all the other terms. And how do the other terms behave? So here we have minus I g mu nu divided by q square, and now times a bracket. So first we get here times 1. What happens in the next? So looking only at the metric tensor term, the metric tensor just gives product of 3 metric tensors. Overall, we get g mu nu, which we already have. So we just get a numerical prefactor. And what is the numerical prefactor? 1 over q square times 1 over q square times pi gamma. So we only get pi gamma, and we get minus I times minus I is minus 1. So we get 1 minus pi gamma. That's just it. Just 1 minus pi gamma. Right? Everything else comes down to this prefactor. So pi gamma is really the correction. And at the next order, with the metric tensors, the same thing happens, and we get just plus pi gamma square, and so on. And then we get minus pi gamma cube, and so on. So what emerges here is a geometric series. Like in first semester mathematics, it's a geometric series, minus pi to the power n summed over n from 0 to infinity. So it's a geometric series, and therefore we can sum it. And the sum is just minus I g mu nu divided by q square, and that gives 1 divided by 1 plus pi gamma. So we get in the denominator times 1 plus pi gamma of q square. That's what happens, and then we have plus q mu terms. So we get a very simple correction to the denominator. That is the result of the photon vacuum polarization. So it corrects basically the 1 over q square dependence of the photon propagator by this factor. At P level, we get 1, but at higher orders, we get the correction 1 plus pi gamma of 0. And therefore, it is interesting to calculate the pi gamma of 0 because it has this important role in modifying basically the interaction strength of the photon interaction, which mediates the interaction between charged particles. So the 1 over q square basically corresponds to the Coulomb interaction, Coulomb force, and so you can interpret this as a correction to the Coulomb force, which is now calculated from the fact. That will be one interpretation and one discussion that we will do, namely what is actually the modification to the 1 over r potential, Coulomb potential. And this is something that you can calculate from here. Now, what we might end up with today is to write down actually the Feynman rules for this photon self-energy. We will not calculate it today, but we can write down the Feynman rules, and then our task for next week is to do the computation and interpret it appropriately. So that is chapter 5.2, computation of the vacuum polarization. And we begin by simply writing down the Feynman rules. And the fundamental object is the self-energy. not the vacuum polarization, so we need to write down the Feynman rules for this minus I times sigma mu nu of Q, the self-energy, which is this one particle irreducible building block here, where the diagram means that the photon propagators are not part of the calculation, only the vertices and the loop. So, and now we need to be specific and precise and write down the Feynman rules exactly. And so, first of all, let's write down that we have a photon momentum Q incoming into the diagram. And then we have here a fermion line going in this direction and a fermion line going in the opposite direction. And by momentum conservation, we don't know which momentum runs in the loop. And so we have here in general loop momentum Q plus K in the upper line, and in the lower line, the loop momentum K flows back. And then you see at both vertices you have momentum conservation. Here Q goes in, K goes in, Q plus K goes out. And similarly at the other vertex, but K is undefined. We have momentum conservation for any value of K, and therefore the diagram involves an integral over the momentum K. So, and now we need to, I think we have enough time to briefly recap the derivation of Feynman rules, which came from a time-ordered product of e to the I times the interaction Lagrangian. And what is important here now are the fermions. So we have for one vertex, we have psi bar gamma mu psi, and for the other vertex, we have psi bar gamma nu psi. And then one fermion line, let's say the upper one, corresponds to a contraction psi psi bar like this. And the other fermion line corresponds to that contraction psi bar psi. Now, the propagator that we have derived for fermions has the form psi psi bar. It does not have the form psi bar psi. Therefore, in order to make out of this time-ordered product the correct definition of propagators, we need to bring that psi bar to this position here. And in order to achieve that, in order to get psi psi bar, which is the normal form of the propagator, but in order to bring that psi bar to that position, we need to anti-commute it 1, 2, 3 times. Therefore, we get a minus sign from the anti-commutators for bringing the fermion psi bar at this position in the contractions. And that is why we get a minus sign from this fermion loop, which is a common thing. Fermion loops generally give a minus sign, and that is the reason here. And afterwards, you see that matrix-wise, we have a contraction, so the spino indices here are contracted, here the spino indices are contracted. If we bring the fermion at the end, it corresponds to taking the trace of the resulting fermion spino indices. And so from this analysis, we see that we get a minus 1 from the fermion loop and a trace of the resulting expression. And using that information, we can write down the value of the diagram, and then we can end. So, minus I sigma mu nu of Q is therefore the following. Minus 1 from the fermion loop times trace of the expression as we just discussed, and then we have the following. We have an integral over the remaining momentum d4k divided by 2 pi to the 4th power. And then we have the rest is just reading of the usual Feynman rules. We use again the rule to go against the arrow, but now it's a trace. We can start anywhere. So let's start, for example, at this vertex. So there at the vertex we have minus I dq gamma mu. Then we take this line. This has the propagator I divided by k slash minus m. Then we have this vertex times minus I dq gamma nu. And finally, we have the upper propagator I divided by q slash plus k slash minus m. So it's a product of 4 factors in the trace. So we get up to 4 gamma matrices in the trace, so it's a quite simple trace that we need to evaluate. But that is the result for the Feynman rules for the photon self-energy, and this is exactly what we need to calculate. And you see it will involve a simple trace and a kind of not very complicated integral, and therefore we can do it next week in our lecture, and then once we have the result, we can do a physics interpretation of it, and we learn all of these aspects that I alluded to. Okay, so let's stop at this point and see you on Thursday for the exercise.